see how to find the count of prime numbers up to a number, say n, which is 12 for example. We will find all the prime numbers up to this number which are less than this number, and we will return their count. And we will be building a solution using JavaScript and also compute the time complexity and space complexity of the solution that we will be building here. The algorithm we have chosen today to solve this problem is called the Sieve of Eratosthenes, and I will explain the concept part before I jump into the coding aspect. So let's start with the conceptual steps of this. Step 1 is whatever input we receive, which is 12 in this case, from the first prime number that we find, that is 2, we will write all the numbers up to this value. So we will say 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We will start from 2. We will say take 2 steps from this 2 and discard the number that you find. So I will say 1, 2, discard, 1, 2, discard, 1, 2, discard, 1, 2, discard, 1, 2, discard. And I have reached my n, so I stop. Next, I increment this value to 3. I see that 3 is still not discarded. I start from here, take 3 steps from here. 1, 2, 3, I discard. This is already discarded. 1, 2, 3, I discard. 1, 2, 3, which is already discarded, and I cannot go any further, so I stop. Then I will move to the next pointer from here to here. I see this is already discarded, so I will just skip it. Then I will move to the next one, which is this one. I will see this is not discarded. I will take 5 steps from here. 1, 2, 3, 4, 5. This is already discarded, and if I try to take further steps, I'm crossing the bounds, so I stop. Then I go here, I see this is discarded, so I just skip. I move on to the next one, and I say take 7 steps from here. 1, 2, 3, 4, 5, 6, 7. The 7th step goes out of bind, so we don't do anything there. And similarly, we try to find other non-discarded elements and try to do the same procedure, that whatever the value, we try to take that number of steps, and whatever value find which is within this bounds, we try to discard the value. So this is the concept, and what we will do is we will translate this into code now and try to come up with a solution. So first step we will do is have an array which will be filled up to n with true. So we say all the numbers by default are being considered true for being prime numbers. This is the initial assumption that we are making. Then what we will do is move on to the next step, wherein we will go here and say that we want to iterate through all the numbers like we did. So we started with 2 and then we iterated. So similarly, what I will do here is I will say start from 2. From 2, I want to go up to n, and I said that I will be taking, for the first time, if this is 2, I take 2 steps. So I take 1, 2, then I discard. And to take those 2 steps, I could have done something like this. 2 star p is less than n, and then p plus plus for the first step. But I also want to make sure that when I am at 3, I want to take 3 steps. So just doing this is not enough. I can just change this to p star p, and this will look more scalable now. So I said that I will iterate. I will be taking steps based on the number that I have received. So if I have 2, I will take 2 steps. If I have 3, I will take 3 steps. And I will iterate through my loop. And then what I will do is I will say that for let I is equal to p star P and I is less than N, I plus equals P. What I want to do is basically say that keep on moving forward, and as I move forward, let's say I'm here. Here this was discarded, so I couldn't do anything here. I just skip the iteration. So what I mean to say is you check if your current value is still not discarded, then you take steps from that value. So before taking any steps, what I will do is first check if my primes of P is equal to true, which means it is not discarded. Only then you take the steps which you are looking for to be taken, and this will be the part that handles taking the steps. So you will say from 2 take 2 steps, from 3 take 3 steps. And what we will doing here is that we have to discard the values whenever we take these steps. So when you take the steps, what we will say is primes of I equal to false at every step that we take. So we will say start from 2, then take 2 steps from there, and then after the value you have reached, after taking 2 steps, take again 2 steps from there. So this mechanism will ensure that happens, and after this is done, we will be left with some values that are discarded, some values that are not discarded. We are marking discarded with false, and by default the non-discarded values which we had will be true because they were initially marked as true. And then what we will do is at the end of this loop we will just iterate from 2 because 2 is the lowest prime number which we can find, and then I will again go up to n, which is going to be the input below which we are trying to find the elements that are prime numbers, and I will say if primes of I is true, then the ultimate goal here is to return the number of prime numbers that you can find below the input number n. Because of that, we will say let's initialize our result to 0. That is going to be the number of prime numbers which you can find, and if this is true, then I will just increment this counter, and in the end I will just return the result that I have received. And that's pretty much it. This is how it converts into the code aspect. And in terms of the time complexity that is involved, it is going to be something like the time complexity is bigger of n log of n. So this is n dot log of n, and the space complexity is going to be bigger of n. Now when it comes to why this is n log of n is because what we are doing here is basically saying we start with 2, we are taking 2 steps at 2, so 2 by n, and we keep taking steps until we reach n, then we reach 3, we keep taking steps until we reach n, 3 steps each. Similarly, we have 5, we keep taking steps. This basically translates into n into 1 by how do we end up with this time complexity of big O of n log of n? What we do is basically we are starting with 2 and we are saying that we are going to take 2 steps from there. Then we take 3 steps from 3. Then we take 3 steps from 5. Then we take 3 steps from 7 and so on until we reach n. What this can translate into is we take the n out, we say 1 by 2, 1 by 3, 1 by 5, 1 by 7, and so on. And this part basically translates to what we said here, which is log of n. So this is log of n, and that's why we come up with this time complexity of n log of n. And in terms of space complexity, it is big of n because we are using this array here to store values until this number that we have received, that is n, up to which we want to find our prime numbers. And then we are iterating through, and here we just update this space that we have used. And in the end, we are just using an iterator here, which can be big of 1 time complexity. Big of n plus big of 1 will just give us big of n. That's why the time complexity is big of n. And that's pretty much it in terms of the solution that we are looking for. Now, we have built the solution, we covered the concept here, and we said this is how it looks in terms of code. We also covered the time complexity, we also covered the space complexity. Now, sometimes we just jump into the solution aspect of it without thinking why we use this algorithm. Now, it will come in your mind saying that, hey, why did this person use the Sieve of Eratosthenes in this algorithm and try to solve? Why not something simpler? The reason being that the simpler approach, which I will demonstrate now, takes higher time complexity in comparison to this one, and that's why we chose this approach to solve our problem statement. What the other simpler approach is that we will be using brute force, and using brute force we will try to go up to the square root of the number that you have and try to find whether the number that you have received, if you do mod of the number which you are trying to reach up to the square root, is giving you 0, that means it's not a prime number. What I mean by that is saying that a prime number is either divisible by 1 or by itself. So if up to the square root of that number, if I'm able to find any number that is divisible by the number itself, that means it's not a prime number. And if I keep doing this to reach a solution, it will be giving me time complexity of big of n square. And because of that, we tried to use this solution which has reduced time complexity. And that's the pretty much reason why we took this approach. Thank you for watching. Please like and subscribe.